In this video, we will cover some additional useful tools and techniques available to you in SOLIDWORKS. These include design tables, which are used to create part configurations, 3D sketches, as well as equations in two different forms, equations used to define global variables, as well as equations that can be used to define curves. Let's first cover the topic of design tables. In order to use design tables in SOLIDWORKS, you will need to have access to Microsoft Excel on your computer. If you do not have Excel installed, I suggest you use the Engineering Computer Lab located in the Sideline Annex to complete the homework assignment related to design tables. First, let's go and create a part. I'll begin by creating a sketch on the front plane, and I'll create a rectangle, adding dimensions to two of the lines. Let's call it 100 millimeters by 50 millimeters. I'll click the confirmation corner, go over to Features, and create an extruded boss, /base. 10 millimeters sounds okay, and I'll click OK. First, let's go over a feature used to display annotations and feature dimensions. On the left-hand side in your Feature Manager design tree, you will find annotations. If you right-click on this, you can select Show Feature Dimensions. By clicking this, the dimensions D1 at Sketch 1, D2 at Sketch 1, and D1 at Boss Extrude 1 are available. That nomenclature means that this dimension, D1, is located on Sketch 1. D2 is also located on Sketch 1. The thickness, which was made by an extrusion, does not exist on a sketch. This value of 10 millimeters exists in the feature Boss Extrude 1, giving the name of this dimension D1 at Boss Extrude 1. At any given time, if we wish, we can redefine the names of these so that we can better understand and refer to these at later dates. Let's double-click the length of this box right here, which is given as 100 millimeters, and you can see in the box above it says D1 at Sketch 1. If you click here, you're free to rename this. I'll rename this length underscore box. If I click OK, I'll now note that this dimension is called the length of the box, which is still defined on Sketch 1. Similarly, I'll rename the dimension D2 at Sketch 1 as width underscore box, and click OK. Lastly, I'll change the dimension for the thickness. Instead of referring to it as D1, I will call it thickness underscore box, and click OK. We are now ready to create a design table in order to make changes to any of these three dimensions. To insert a design table, go up to your File menu, go to Insert, then go to Tables, and select Design Table. When you're creating a design table, the following property manager comes up. You can change the source, edit control options, and additional parameters. I'm going to leave all of these at their default values and click OK. Two things have now happened. First, a box appears which asks you to select the dimensions to add to the design table. You'll note that there are three that have auto-populated here: the length of the box, the width of the box, and the thickness of the box. These have taken on the names that we have just previously applied. Had we not applied these names, these would appear as D1 at Sketch 1, D2 at Sketch 1, and D1 at Boss Extrude 1. I find that by naming these values, it's much easier to pick out what dimensions you wish to include in your design tables. I will select all three by holding down Control and clicking all three of those dimensions, and then selecting OK. You'll now note that superposed in your graphics area is a design table, which comprises an Excel spreadsheet. If you were to click anywhere outside of the design table, you would exit the Editing Design Table panel. Since I wish to create new dimensions within the design table, I will not click anywhere outside of the design table box. Looking at the design table now, the column headers read the dimensions that we wish to change, and the row headers start with only a single row with a configuration named default. These are the default values that you initially populated in your drawing. I'm going to go ahead and create what's called a new configuration. First, by titling the new configuration, I'll call it New Box. And maybe another one, New Box 2. Perhaps a third, New Box 3. In the cells in the Excel spreadsheet, we are now free to insert numerical values for each of these feature dimensions. For example, perhaps New Box will have dimensions of 100 by 50 by 20, doubling its thickness. Perhaps New Box 2 increases in size by a factor of 2, 200, 100, and 20. And perhaps New Box 3 goes as 200 by 100 by 10. You can continue to add new configurations as you desire. If you have a feature that does not need to change in your design table, simply don't include it. I'll now click outside of the design table in the graphics area one time. SOLIDWORKS will now indicate that the design table generated the following configurations: New Box 2, and New Box 3. To find these new configurations, go to the Configuration Manager, located 2 tabs away from the Feature Manager. In the Configuration Manager, you will find the default part, which has a green checkbox indicating that it is being displayed in the graphics area, as well as New Box 2, and New Box 3, which are all currently grayed out. If I were to double-click on New Box, the dimensions would now change according to how they were defined in the design table, and this has been reflected in the graphics area. Similarly, I can select New Box 2, which will show New Box 2, and New Box 3. At any given time, you can go between these 3 different configurations, or go back to the default configuration. If you wish to edit your design table at any time while within the Configuration Manager, expand Tables folder, right-click on Design Table, and go to Edit Table. A screen may pop up asking you to add rows and columns. In this case, I will click OK without adding any additional rows or columns. By adding additional columns, you would be adding additional dimensions or features that you may wish to change in your configurations. Additional rows would correspond to additional configurations. Here you can make any changes you wish to any of these dimensions. Once you're happy with your changes, simply repeat our prior procedure and click anywhere outside in the graphics area. Once again, you can now go through the various different parts that have been created using the design table. The design table allows you to easily create families of parts whose geometries are related by the features and dimensions that are shown. Suppose you did not want to manually change the values that you see in any of these given dimensions. You can use what are called global variables to create linked equations that change values relative to other values. For example, let's go ahead and make a new part. And as before, we'll create a new sketch on the front plane. And give it similar dimensions, although these will be placeholders for the moment, of 100 millimeters by 50 millimeters. We'll confirm and extrude this out some distance. As before, we can display feature dimensions by right-clicking on Annotations and clicking Show Feature Dimensions. Now we can use what are called global variables to drive some of these relations. If I double-click on this D1 at Sketch 1, I can do two things. First, I can rename D1 length underscore box as before. Additionally, I can change and create what's called a global variable. In this area, where you normally specified simply a numerical value, we will now create what's called a global variable. We can do so by typing the equal sign, a set of quotations, and the name of the global variable. In this case, I will also name the global variable length underscore box. Closing quotations, we now have a new glyph that looks like a globe. If you hover over that, it reads create global variable. If we click this, we will now have created a global variable with a shared name that is also length of the box, length underscore box. You can toggle between the current numerical value and the linked global variable by clicking on the toggle global variable / value display button. I'll go ahead and click OK. Note two changes have occurred when we have created this global variable. First, there is a new symbol appearing before our dimension. This is a red capital sigma. This indicates that this dimension is linked to an equation. To see that equation, you can now go to the Equations folder, which has now appeared in your Feature Manager design tree. You can right-click that and select Manage Equations. By doing so, you see all of the equations inside of our sketch. For example, under Equations, we have length of the box at Sketch 1 being equal to the global variable, the length of the box. That global variable, length of the box, has a value of 100. And as a result, the length of the box at Sketch 1 dimension is set to 100. That's the simplest form of an equation that can appear in SOLIDWORKS, simply stating that a single dimension is equal to the global variable, and that global variable takes on a numerical value. We can relate additional global variables to that initial global variable by using additional equations. For example, suppose we wanted this dimension right here. If we double-click this, D2 at Sketch 1, we can also call this width of the box. And as before, rather than setting a numerical value, we can create an equation to drive this value. First, we can create an equation by hitting the equal sign, where we'll find the following. We can scroll down to Global Variables and find all of the global variables with their current numerical values, which are now selectable. If I select the length of the box value, it will insert in quotations the name of that global variable, being length underscore box. If I were to select OK now, this would drive the width of the box to take on the same value as the length of the box. In this case, I'll modify our equation to be the length of the box divided by 2. If I now click OK, we will now see that this value also now has a red capital sigma symbol, indicating that it is driven by an equation. We can repeat this procedure for the extruded thickness to modify the thickness to be, for example, under global variables, the length of the box divided by 10. I'll go ahead and click OK. And let's revisit the managed equations. We'll now note that we have 2 additional equations that have been added in, all referencing the original global variable, that the width of the box is equal to the length of the box divided by 2, and that the thickness is equal to the length of the box divided by 10, although I've forgotten to rename the variable d1, which I'll go ahead and fix now. You can drive global variables in design tables to create additional configurations. To create configurations based upon changing global variables, we'll go by starting first by inserting a design table, by going to Insert, Tables, Design Table. I'll keep the settings in the Design Table Property Manager at their default values and simply click OK. As before, SOLIDWORKS will ask us which dimensions to place in the design table. In this case, I will not make any changes to these dimensions. I'll click OK, and SOLIDWORKS will provide us with a blank design table. The first cell that's highlighted by default is cell B2. This is where we will enter in the following syntax in order to modify the global variable named length_box. The syntax is $value, written in capital letters, at, and now we insert the name of our global variable, in this case length_box. And finally, at equations. In other words, SOLIDWORKS has created the following syntax in order to change the value of the global variable named length_box located under equations. If I click Enter, you'll note that this is our now column header. We can now insert our default configuration by setting this value to 100. We can now create another configuration, new box 1, and change this value to 200. And similarly, new box 2, we can change to 400. And finally, new box 3, we can change this value to 800. By clicking anywhere inside the graphics area, SOLIDWORKS will now create the design table and the 3 new configurations based upon that design table. As before, we can navigate to the Configuration Manager and double-click any of the new configurations to see our new boxes. If I double-click on new box 1, we'll note that we've driven 3 different dimensions simply by changing the global variable known as length_box. The length of the box has increased by a factor of 2, as has the width and the thickness. We look at new box 2, we've increased these values again by a factor of 2, and in new box 3 we've increased these values again by an additional factor of 2. By changing dimensions and by using global variables, you can have a tremendous amount of flexibility in creating new part configurations to be able to create families of parts that feature related geometries. Moving on, now let's take a look at 3D sketches. We'll start by creating a new part, and note that if we were to create a regular sketch, by default this is a 2D sketch. When clicking on Sketch, for a 2D sketch you must select the 2D plane on which the sketch will reside. That could either be one of the 3 default planes or any plane defined by a flat surface existing on geometry that already is present in your graphical area. If instead of clicking Sketch, we hit the down arrow, we can now create a 3-dimensional sketch, or 3D sketch. Note that when we create a 3D sketch, SOLIDWORKS no longer asks us to define the plane on which the 3D sketch will reside. That makes sense because the 3-dimensional sketch features lines that reside on multiple planes. To get started, let's go ahead and click the Line tool. We'll note that when we bring the tool into the graphical area, we'll see our familiar pencil glyph, which indicates that we are going to be creating lines, underneath which now has a new symbol. By default, it says XY. The XY indicates that we are going to be creating lines that exist on the XY plane. For example, I'll start by clicking at the origin and creating a horizontal line and then a vertical line. If I hit Escape to exit the Line tool, I can now rotate about, and we note that we have created 2 lines that exist on one plane, that being the XY plane. If I now go ahead and click the Line tool again, when I bring it into the graphical area, I can hit the Tab key. Hitting Tab toggles between drawing on the XY plane, the YZ plane, and the ZX plane. I'll now begin by drawing lines on the YZ plane. I can then create lines that exist on the ZX plane. By zooming out a bit and rotating, we can clearly see that we have created lines that now exist on multiple planes, all residing within a single sketch. We have access to all of our normal sketch tools. For example, I can click on Sketch Fillet. Using a sketch fillet, I can add, for example, a 50mm fillet that connects those 2 lines. 50 is too large. I can decrease that by a factor of 2, down to 25mm, and add additional fillets between other lines. SOLIDWORKS is smart enough to be able to figure out on what plane the fillet should reside. However, this requires you to properly select the 2 lines between which you wish to create your fillet. If I click OK, we now have smooth transitions between all of these lines. "3D sketches such as these are most often used to create sweeps, where the 3D sketch defines the path for the sweep, and a second 2D sketch is used to define the profile. If I click OK, we can now create another sketch, the 2D sketch, for a profile. If you don't have a readily accessible plane on which to create your 2D sketch for your profile, recall that you can always go to Features, Reference Geometry, and click on Plane. We can do this to create a reference plane. One of the simplest ways to do so is to click on the endpoint and the line that connects to that endpoint. This will fully define a plane that is coincident with this endpoint and that is perpendicular to this line. If we click OK, we now have a plane on which we can create a 2D sketch. In this case, I will create a circular cross-section and give it a dimension, let's say 5 millimeters. If we wish, we can also add a second circle and dimension this to be slightly larger. In this case, let's make it 7.5 millimeters and click OK. We now have a profile that consists of two circles that are concentric to one another and a path defined by our 3D sketch. We now have everything we need to go over to Features and to create a swept base. To define our profile, we can simply select our 2D sketch. To select our path, we can select our 3D sketch. If I now click OK, we can see the resultant part. If we right-click on the newly created sweep, we can go down to Change Transparency. If we click on Change Transparency, all of the geometry created by this sweep feature is now transparent. Note that we have swept two concentric circles, the result of which is a hollow tube. In other words, the area defined as the region between these two circles defines the solid geometry that has been swept out. We may also use equations to create lines, both in 2D and 3D sketches. We'll return to the 3D sketch in a moment. First, let's create a new part and try to create an equation-driven curve on a 2D sketch. We'll start by creating a sketch on the front plane. To get to equation-driven curves, navigate up to the Spline tool and click the down arrow. You can either create a spline or an equation-driven curve. Equation-driven curves come in two varieties, on 2D sketches at least. They can either be explicit curves. In this case, y is given as a function of x, or as a parametric curve, in which case both x and y are given in terms of a parameter. By default, that parameter is t. To demonstrate, let's use an explicit equation. Y is a function of x. To enter an equation, we can write, for example, x squared minus 4 asterisk x for 4 times x plus 4. You must set a range for your parameters. I'll go from x equals 0 to x equals 5. If I zoom in, you'll see a curve that looks like this. Click OK. You'll now have a fully defined curve that exists within your sketch. Note that this curve is fully defined with respect to the origin. This means that it should not be able to be moved around unless you were to click on the equation or click on the feature and modify the equation. Modifying the equation will allow the position of this curve to change from one location to another. I'll go ahead and add some lines now in order to create a closed contour. With this closed contour, we can now create features. If I say OK and exit the sketch, I can go back to features and create a revolved base. I can use this line as our axis of revolution to create a shape. If I click OK and show you a cross-section view, you can see a cross-section of the shape that we've created, where this curve here is defined by our parabolic equation. Equations can also be used in three-dimensional sketches. For example, if I return to our 3D sketch that was used to create our sweep, if we wished, we could add additional equation-driven curves into our three-dimensional sketch. This works in much the same way as in the 2D sketching. We return to the spline tool, click the down arrow, and go to equation-driven curve. For a three-dimensional sketch, you can only use a parametric style equation. This requires you to define x, y, and z all as a function of your parameter t. For example, I can create the following. X could be our parameter t. I will divide this by pi. Pi is written as capital P, lowercase I. Y of t can be written as some number, say 50, times the sine of t. Z could be a similar number, say 50, times the cosine of t, where t varies from minus pi to positive pi. We'll note that this has created the following curve. If we click OK, we can get a better view of the newly created three-dimensional curve. At any time, we can modify these equations by clicking on the new equation-driven curve and changing these values. For example, I can increase the apparent thickness of this loop by a factor of 10. I can rotate this loop by adding in a phase offset of, for example, pi divided by 2 in both y of t and z of t. Once you're happy, you could connect this to the original line to continue your sweep. We can additionally add sketch fillets. and attempt to reconstruct the sweep. In this case, there's an error. The sweep could not be completed because it intersected with itself while passing through a segment on the path. In other words, the cross-sectional profile that is being swept, given by our 2D sketch here, is too large with respect to the radius of curvature on the newly added sketch fillets. We could, for example, change these values to 1 millimeter by 1.5 millimeters and click OK. This allows you to successfully reconstruct the entirety of the sweep without having any geometrical errors associated with tight radii of curvature. The final feature that I wish to showcase in this video is called the Combine tool. You've already been exposed to what are called Boolean operations. Boolean operations allow you to create intersections and unions of solid models. Anytime that you've used an extruded boss/base, revolved boss/base, or swept boss/bases, you've been creating new material which is often merged to the underlying geometry. This is an example of Boolean addition. Similarly, every time that you've used a cut feature, this is an example of a Boolean subtraction, by removing one component from another. Anytime that you have an easily definable sketch, these are very convenient tools in order to use Boolean operations to create your components. Often, it is not convenient to utilize these features. For example, when you have a very complex geometry that requires significant amount of labor to be able to use reference geometries in order to define the proper planes and sketches with which to create these features, you may want to use what's called the Combine tool. Let's show you an example of how this tool works. I've created two parts. Part 1 I've named Mold 1, which is a simple block. Part 2 is this thing that I have created. It's a complex shape. You can see how it was made on the left, using revolves, extrudes, fillets, sweeps, and circular patterns. The question becomes, suppose that you wanted to create a cavity within this block that mimicked this geometry. How would you go about doing that using extruded cuts, revolved cuts, or swept cuts? It would be a difficult task. That task is made significantly easier by using the Combine tool. The first step in using the Combine tool is to create an assembly file. Here, I've created an assembly in which these two components have been positioned relative to one another using mates. Mold 1 is fixed, and the position of Mold 2 was placed within Mold 1 by creating mates, in this case distance, tangent, and coincident mates. If I were to go to a wireframe view and change to a top view, you can see that this component is immersed halfway within the mold part and roughly centered on the face. In order to next use the Combine tool, we have one more step. You must go up to File and go to Save As. The Combine tool could only be used in part files, not in assembly files. Therefore, you must take the assembly and save it as a part file. Once you save it as a part, you'll be able to use the combine feature. Be sure that you select under Geometry to Save the notion All Components, which will save all of the components in your assembly into a part file. So I will call this part mold assembly demo. Being sure to click on All Components under Geometry to Save, I will now save this as a part. When using Save As, you are creating a copy, which means that part is not yet open. If I were to close all three of these parts and locate Mold Assembly Demo, I can now open this up. SOLIDWORKS by default will ask you, do you wish to proceed with feature recognition? I'm going to select No. We will not need feature recognition in order to use the Combine tool. Note in our part, which is now called a multi-body part, we have two parts labeled Mold 1, Solid 1, and Mold 2, Solid 1. Note that you cannot expand these out. You can no longer see all of the features that were utilized to create each of these individual components, nor can you easily move them once you've saved this as a part file. I highly recommend that you therefore save your assembly file separately so that you can go back and modify positions as necessary. We are now ready to use the Combine tool. If you do not have the Combine tool in your command feature bar, go to the upper right-hand corner. You'll see a magnifying glass. If you click the down arrow, you'll have a number of functionality changes that can be used for the command search box. By default, yours might read SOLIDWORKS Help. By clicking on the down arrow and changing the functionality of this box to Commands, you'll be able to issue commands directly to SOLIDWORKS. Once you've done that, type in Combine. You could either directly select Combine from this search bar in order to access the Combine Property Manager, or you can click and drag this onto your Command Manager for quick access in the future. If I click on the Combine tool now, we have a simple box where we have to define the type of operation, either addition or subtraction. In this case, we'll do subtraction. You'll be asked to define the main body. In this case, the main body will be the body that remains after subtraction. This is the body that I would like to remain after subtraction. Under Bodies to Combine, this will be the body that we subtract from the main body. If we now click OK, we now have the following. If I go to a wireframe view, you can note that we have created the following geometry with a complex cavity existing within Mold 1. You can now save this part and utilize it in further endeavors. I highly recommend that you check out 3 tutorials. Navigate over to Tutorials. Under Basic Techniques, you will find Design Tables. Under Advanced Techniques, you will find Equations, as well as 3D Sketching. Each of these tutorials is relatively short, and you'll learn a great deal